theories of atoms, electrons, and birational geometry. So, I mean, I had an ample opportunity to study birational geometry from the best in the field, including Iskovsky, Shukurov, Mausley, of course, my classmates like Alexeyev, Pukhlikov, Prokhorov, and then later by Moore and Kuar, but I never learned it. So, and let's see, I mean, at old age, what one can actually learn. So we will say that X is a projective variety. Let's say over the complex numbers over some field K, which we'll consider. And so we say that X is rational if the field of rational functions of X is isomorphic to the field of rational functions of n variables, where n is the dimension of X over C or over K. In other words, if there is a birational transformation between X and Pn, we will say that X is rational when its field of rational functions is the same like the field of rational functions of Cpn. So now this is a question about rationality. Is a very old question in birational geometry, and so when I was learning birational geometry, to be precise, when I was trying to learn birational geometry, so the questions that were considered as the following. So let's say that X is a smooth cubic in P5 or the complex number. And so the question was, is generic X rational? In other words, this generic four-dimensional cubic over the complex numbers birational to CP4. So another question was, if you take Grassmannian to 5 and then you intersect it with a quadric and the plane, both all embedded in P9 by Brucker. So so is this four-dimensional manifold actually, so it's called Gushov-Mukai manifold. It's generic Gushov-Mukai manifold rational. So now we can intersect this with one more plane. And becomes three-dimensional, and so the question is every sorry, actually in this case, not rational. It's known that some of the generic one is not rational. The question is every is not rational. So then, now that I see that the IT is here, I remember the following question that was also considered at that time. So you can actually change the field and consider varieties over non-close algebraically non-close fields. So in particular, you can take P1 cross P1 cross P1 cross P1 and consider the hypersurface of type 1, 1, 1, 1 in it. So over the complex numbers, this thing is just blowing up P1 cross P1 cross P1 in an elliptic curve, so it's very rational. But if you consider this over a field K, this is the Galois group of K, subjects over S4. So this is algebraically non-closed field with such a Galois group. So you can ask if this hypersurface, this three-dimensional Fano variety, is actually rational over such a field. And I think that for generic one, sorry, for everyone, it's still not known. For some of them, that's proven. And then, of course, you can increase the number of P1s and 1s by 1, and then I think the answer of this question is not known. And then let's go one dimension higher. So let's say that you have a two-sheeted coloring of P5 ramified in a quartic. So the question is this rational? So now in these questions that I not pointed out here, I learned from Iskovsky. Well, this is probably older. So it's like Leonardo da Vinci. So now these were the questions that people were talking about around 1985. And the last time I checked, well, I could be wrong, no matter that a lot of work was done by many people, Poisson, Couloir, and then all the derivatives, including the field, not much actually is known about the answer of this question even today. And so what I would like to propose is an approach to this based on a method that was discussed by Andrei in his talk, and that is using the method of B-modules and their singularities. So, I mean, in order to do this, I'll start with some examples, and then I'll formulate a theorem and technique which will actually give us the opportunity to answer this questions. So now, so of course, the idea for all this is based on mirror symmetry, but we will not use any mirror symmetry in the actual calculations. I need to give you at least some reason to, in order to see where this all comes from. And so let's start with some very simple manifold, which is definitely birational P2. And so the birational geometry of CP2 is basically geometry of points in CP2 which get blown up and blown down. And so let's actually try to explore how this is recorded by mirror symmetry. So the mirror symmetry of CP2 is to this subjective variety will correspond to an open subjective manifold, in this case C2. And a function W, which it's called the potential. And now the point here is that you can associate to both sides of this correspondence categories. Here is a category of sheaves, so on P2, category of coherent sheaves on CP2, which is generators. And here you actually correspond to these symplectic objects. And so basically this is a vibration of open elliptic curves, which has three singular fibers in the finite part. And then if you choose another smooth fiber, you can choose one cycle in this elliptic curve, open elliptic curve, and then choose a path on W direction, and then homotopy this cycle in different paths. And so you get three Lagrangians, and the mirror symmetry proven in this case tells you that this category of coherent shifts you can correspond to a category of Lagrangians, and they happen to be equivalent. Now, the things to notice is that if I blow up CP2 in one point, so what's happening on the level of category, I add one more exceptional object, and actually on level of this mirror, I add one more singular fiber, and the corresponding category becomes generated by four Lagrangians. So now the thing that you need to remember is that blowing up on this side, on the algebraic side, the side that we want to study, amounts to creating one additional singular fiber. And basically what we want to do is to remember that these new things that we blow up, they create new fibers, and they do not interact with each other. So now, although mirror symmetry is proven for P2, that was done, I'm not mistaken, in 2006. Paper appeared in 2008. So now, I mean, I don't think we can prove mirror symmetry, especially in these cases that I have outlined here. But what one can do is, you really care about this points over which you have singular fibers. And if we can avoid this mirror symmetry, talking about categories, and only work with these singular fibers, you actually might be able to get some interesting consequences. And that's what we will try to do. So what we need to remember is that there is such a thing which is called quantum differential quantum D-module associated with a symplectic manifold and its Gromov-Witten theory. So first, we will think of X as an algebraic variety with the RAM theory on it. And then we'll take we'll think of X as a symplectic manifold. And to this symplectic manifold, we will associate differential equation, and we will remember the singularities of this differential equation, and that will allow us to put a new splitting on the de Rham homology of our algebraic variety. So this differential equation is of this type, so you can think of u as the variable here on the Van Ginsburg model. And so the solutions of this differential equation, just in the previous talk, has a lot to do with the Gromov-Witten theory associated with our manifold. But we don't want to think so much about the Gromov-Witten theory. We only need to remember the singularities of this differential equation, which happen to be precisely corresponding to the singularity of these vibrations of Calabi-Yau, which I have emphasized at this example. So once again, we will forget about mirror symmetry. We just put this differential equation on the, sorry about that, our initial manifold. So our initial manifold is not as an algebraic variety, but we associate to it this D-module, this quantum differential equation as a symplectic manifold, and the solutions of, sorry, the singularities of this differential equation are going to be used as a additional birational invariant. So now let me do a little bit non-trivial example. The first non-trivial example in birational geometry, this is the example of three-dimensional cubic. So it's exactly like this one, but just one dimension lower, dimension t. And this example was worked out by Philip, who is not around today. He's on his well-deserved vacation somewhere in the Caribbean. But so let's remember him by bringing this example that he has worked out in 1972, actually mainly by Clemens, the king of the monodromy map. So we consider the following example. And so the way Clemens and Griffiths prove that this is not rational, so they introduce the so-called intermediate Jacobian. So a biliary variety obtained by this such algebraic group. And so there was this very deep study by Andreotti and Meyer on the singularities of the theta divisor of this modular spaces, modular space. And I mean, if these singularities of this theta divisor turn out to be too small, so in this case, they were just zero-dimensional, just a point. So this cannot be a Jacobian, and then that's the way Clemens and Griffiths concluded that this cannot be obtained from P3 by blowing up a curve, because if that was the case, this was going to be a Jacobian, and that certainly is not the case. So now we'll look at this example in a little bit different way. So now classically, we would have just worked on the this side, and at the end of the day, that's exactly what we are going to do. But let me just briefly tell you that in this particular case, this mirror is given by the following function. And so if we open clear the denominator, this is a family of open K3 surfaces, which has three singular fibers. So two of them are K3s with just ordinary double points, but there is a very singular fiber, which is intersection of 6 rational surfaces with this open book configuration. And so in this case, and I'll just tell you what this equation looks like. So K is, this is the quantum multiplication in this case. It's 4 by 4 matrix. And G is just a normalization. And so this ordinary differential equation has 3 singularities, and so the model has 3 singularities, and actually its solutions have very interesting asymptotics, which we'll consider in a second. But the important thing is that there are 3 singular points indeed in this equation. And in fact, they precisely correspond to the singularities of this vibration of K3 surfaces. And what we will do.
And you measured how bad the singularity is with something in the equation. I don't know how.
So
rational singularity.
Well, so the first, I don't know what rational means. This is the singularity of the differential equation, not of the. But I mean, there is a meaning in what you are asking. So you could ask if this singularities are regular or irregular. If you actually come up with an equation which is irregular singularity, that would definitely be abstraction to rationality. But so in any case, so what we can see in this classical example is the following. So let's think a little bit more of the rank homology of this three-dimensional cubic. So this is the Hodge diamond, and so it looks like we have taken P3 and have blown it up in a curve of genus 5. So in fact, there is a theorem which we proved a long time ago with Mark Gross and Helge Rudat, whose name was mentioned in the first talk, saying that if you take this Landau-Ginzburg model and compute the perversive of, hyperhomology of the perversive of vanishing cycle associated with it, you're just going to get pretty much this Hodge diamond with some modification, which makes me think that actually there is some deep connection there, but I wanted to avoid mirror symmetry at any cost. And so what we have here is that homology of this cubic splits in 3 pieces. So this one corresponds to this piece of the Hodge structure, which looks like the Hodge structure of human surface, but the other two are just one-dimensional. And so that is the splitting that we get out of the singularities of this quantum differential equation. And indeed, so the following theorem which you heard a lot about 2 weeks ago, tells you that so for every funnel, so there exists splitting of its homologies indexed by eigenvalues of quantum multiplication by the canonical class and up to contributions of subvarieties of codimension 3 and higher, this splitting is a birational invariant. So now, in other words, what we are saying is that if we forget about contributions of varieties of codimension 3 and 5, or these points that we have here, so this, in this case, is the birational invariant. And so now, if we can actually show that this is not connected with the Riemann surface, then of course we can show that this three-dimensional cubic doesn't come from blow of P3. So the problem is that it very much looks like it comes from P3 blow, not in a genus 5 curve. So we need to do something else. And indeed, what you could do is you could actually compute how this so-called surfunctor acts on these two homologies. And that is actually easy. So that in all of these cases was computed by Orlov, Bondel, and Kuznetsov. So then you will notice that St in power 3 is a shift by 5. And that's not how the surfunctor acts on the homologies of Riemann surface. So that's how you conclude that this piece cannot be associated with the Riemann surface. Therefore, the three-dimensional cubic is not rational. That's a different proof of the notorious theorem by Griffiths and Clemens, which I mentioned here. So now this method can be used in other cases, but you really need to be able to get the information coming from the Landau-Ginzburg model, which are known in many cases, to be useful for these splittings. And here really a fantastic service was done to the society by Giventhal, whose actually there was a fantastic moment in the history of Caltech, where for 2 quarters, Andrei, Rahu, and Giventhal were in Caltech. No,
was it?
Really? Oh, maybe Berkeley. Okay, but I remember that. So first of all, so there was very strong Whitten presence there. On the top of that, initially Whitten and then Michael Douglas were in Whitten in very short period. So this is why I got convinced that maybe the symmetry can be used for birational geometry. But then this is like this for me like well justified belief. It's like this philosophical interpretation that you walk in the desert and you believe that there is a water somewhere. So you see this mirage and you come to the place and actually there is nothing there in the desert. But if you dig down and use an excavator, you are actually correct. There is a water in this place. And so all I needed to do is to find a strong enough excavator like this guy here, who can find a water even if there isn't one. And so that's anyway, all this result was obtained. But so so the theorem of Giventhal's, which has a really terrible name, if you ask me, which is like the quantum lectures or something like that. But the point being here is the following, that you have this Landau-Ginzburg model, and you have so this D module, which I told you so. And you have the D module associated with the so-called Landau-Ginzburg model. And so what Giventhal tells you is that after Fourier transform, these two D modules are equivalent. Module how is this called? Birkhoff transformation. So, and indeed, what that means that whatever you can find out about the eigenvalues, which like the singular points here, and even much more, will be you'll be able to relate to what is happening in this quantum the module. So if you have different eigenvalues, then you have different eigenvalues here. So I'm putting a little bit things under the rug here, because one needs to really introduce this Frobenius manifold and these parameters, and the splitting should be defined over generic point of this Frobenius manifold, and becomes even more interesting if you actually start moving And there is this dynamic of these eigenvalues, which will tell you quite a bit. But all these examples that I wrote on the board, with the exception of the fourth one, have picard equal to z, and therefore this interesting phenomena is kind of lost. So if you can show the splitting in one point, then everything is fine. So let's, in the remaining time, we'll look at some of these examples that I have pointed out here. So first, the four-dimensional cubic. So so in this particular case, if you compute the corresponding Landau-Ginzburg model, so you will see that we have four singular points, and therefore the splitting of this Hodge diamond is going to look like that. So now all we need to do is to analyze what's happening here, because these are really one-dimensional, and modulo may have really big codimension. But actually, the thing that is happening here is that you have splitting really of this 21, 1, and this 21 actually splits as one more cycle separates. So, and all you can notice here is that we have some Hodge diamond that looks like Hodge diamond at a K3 surface. But what you could do is notice that, in fact, this Hodge diamond has only two algebraic cycles. And every algebraic surface has at least three. Every projective surface has at least three algebraic cycles. Therefore, this cannot come from a blow up before. So that's how you conclude the generic four-dimensional cubic is not rational. So of course, experts can immediately notice that if there is additional algebraic cycle there, this argument will not work. So you have three, and then the argument which I just proposed for this having only two algebraic cycles will not work for non-generic cubics. So particularly the cubic has additional plane, then this argument is lost. So now let's do one more example. This is like you really like these examples a lot. So it's not going to be a question about birational geometry, but it's going to be about equivariant birational geometry. So we are trying to answer if this 1, 1, 1, 1, 1 hypersurface has can be obtained from P 3, or rather rational threefold, by blowing up. Well, as I told you, over the complex numbers, this is known to be rational. In fact, it's a blow up of P1 cross P1 cross P1 in an elliptic curve. But let me demonstrate. So this is a question which, as I said, was posed out long time ago by Stosky, and was partially answered by Kuznetsov and Prokhorov. But you can actually get a full answer here by the following argument. So if you over the complex number, so the splitting so this has huge pk, obviously 4, and so the splitting actually so looks as follows. So we have Hodge diamond which looks like that, which splits on so we have this elliptic curve, and we have 4 other pieces which are one-dimensional, and so this is over the complex numbers. But now, if you consider this to be over different field, and then you have a Galois group which surjects over S4, or you actually want to consider birational geometry, which is only S4 equivariant, so this pk becomes 1, and you cannot really split it on so many pieces. In fact, you have only four pieces like that. Sorry, yeah, like that, and so you have a splitting like that, and so you can actually this is due to the S4 action, and so there is no way that this piece actually could come from a Riemann surface by the way it looks like, and then you have only one-dimensional direction in which you could deform it, so it will stay like that. And so this is how you conclude that this 1, 1, 1, 1 hypersurface is not S4 birational. To P3. So it's either not equivariant birationality, or you could say it's not a birational to P3, but over this field with Galois group which surjects over S4. So you can do this for 5-dimensional varieties. So now a very interesting application is this 5-dimensional one, where so this is a combination of really deep knowledge of minimal model program and the combination of Gromov-Witten theory. And so it is based on the following observation that if you have a variety of dimension, I mean, so it's a fact of minimal model program, which is proven only, I mean, I believe it's true in general, so it's not me, it's Kolar and Ricardo believe it's true in general, but it's proven only up to dimension 5. So, and it says that if you have a minimal model program, sorry, if you have a variety with non-trivial section in its canonical class, you can find a minimal model which kfx positive, where kfx is positive. And so this fact, in combination with Gromov-Witten theory, allows you to carry calculations like that for varieties up to dimension 7, 5, and then codimension 2 up to dimension 7. But I mean, if people a minimal model program actually can prove this in higher dimension, then this method will work in higher dimensions as well. So I'm not sure which one is harder. So in any case, so these pieces here actually are called atoms, but they can be given additional characterizations. In fact, what one can do in the case of Banach manifolds is take this piece, the atom associated with 0, which is uniquely pronounced in the case of Fanos, and restrict this D module, quantum D module over it. And then this quantum D module has solutions which has asymptotics. And so that these asymptotics are actually also birational invariants. And so they are nothing else but the eigenvalues of the monodromy around these most singular fibers that I have mentioned here. And that's why I propose to call them electrons, because this is a joke. But in any case, these numbers are birational invariants. So let me show how this works in general. So the following theorem is correct. So this, the first one, the biggest one, we'll call sigma. So let X be a Fano hypersurface of degree D in P, careful, n minus 1, then delta is equal to dimension of x minus 2 times n minus d over d. And so the theorem number 2 is that if delta is bigger than dimension of x minus 2, then x is not rational. So this is just the first number. I mean, so we could do stipulation using the dynamics of these numbers to formulate other criteria. But I mean, I won't go into this now. But so now this is a subject which was actually developed very much exactly when this, at least I was aware of these questions, 1984, 1985, since these numbers are nothing else but so-called R charges in the corresponding conformal field, massive conformal field theories. And so, I mean, approximately at that time, when I was learning that this question exists in birational geometry in Moscow, some logical techniques were developing this charges in the conformal field theory. So they are very hard to compute in the massless case. So if you know how to compute them, you buy a ticket to Stockholm. But in the massive case, when there is a geometry, that's easier, and that's what in a way is used here. So let me just finish by applying this criteria to our favorite cubic threefold. So in this case, we have d is equal to 3, and n is equal to 5. So it's a cubic in P4. So let's see if I haven't made a mistake. So we have delta is 3 minus 2 yeah, it's 5. So delta is equal to 5/3, certainly bigger than 1. And according to the second statement, we prove this theorem of Griffiths once more, and we see that the three-dimensional cubic is not rational. So now you can easily see that in dimension 4, this number is actually equal to 2. So it doesn't help you with the 4-dimensional cubic. But if you go deeper and do this analysis with algebraicity of the what is you can actually show the non-generic one. You have this type of behavior. All right. So hopefully I certainly couldn't come any close to what Alexeyev would have done, but that's it. So let me stop here. So we'll continue tomorrow at the same time.
So this does not answer question 1, right?
It does. Meaning this delta?
Yeah.
No, that doesn't. But there was this previous argument which we considered with this splitting, and there was the this piece here, which happened to have only two algebraic cycles in it, and every projective variety of dimension 2 has at least 3. So, so it's very similar here, actually, for this Gushev for manifolds, which also we can show the generic one. Dimension 4 is not rational by the very same. So, I mean, there was supposed to be a dinner tonight, and we can go, but we need to find Andrei somewhere. So, it's a dinner in his honor. Let me, who wants to go to dinner? Julia?
I'm indifferent.
Okay, so let me try to